The darkness between galaxies holds more than we ever dreamed. For decades, we mapped the cosmos and labeled these vast regions as empty voids, but that was a profound oversight. This journey uncovers 20 distinct clues hidden in those cosmic shadows, each one challenging our most basic ideas about the universe's structure. You will discover how unexplained gravitational lensing and strange radio bursts from nowhere are forcing scientists to reconsider everything. By the end, you will see the entire cosmos not as isolated islands of light, but as a single, connected web buzzing with hidden activity. What if the greatest mysteries are not in the stars, but in the silent spaces we chose to ignore? How much of the universe's true story remains untold in the darkness? What does it mean for our place in the cosmos when even the emptiness is alive? Our first maps of the cosmos were drawn with blurry vision. In the early 20th century, astronomers peered through their telescopes and saw a universe of bright islands scattered across a dark sea. Their instruments, revolutionary for their time, simply could not see the faintest glimmers in that profound darkness. The vast tracks between galaxies were labeled as voids, empty and uninteresting. This was not a careless mistake, but a necessary simplification born from technological limits. The prevailing model of the universe was one of distinct structures, where galaxies were the main characters, and the space between them was just the empty stage. The word empty became a convenient scientific shorthand, a way to classify what we could not yet perceive. It was a label that stuck for generations, inadvertently blinding us. By deciding these regions were barren, we stopped looking for what might actually be there. We programmed our surveys to ignore the shadows, focusing only on the brilliant points of light. This historical oversight created a perfect hiding place for clues we are only now beginning to find. The very definition of emptiness we relied upon is what kept 20 profound secrets waiting in the dark for a century. The first crack in the illusion of emptiness came from the oldest light in the universe. Satellites like Planck and WMAP were meticulously mapping the faint afterglow of the Big Bang, the cosmic microwave background, when they found something deeply puzzling. In the vast, supposedly barren tracks between galaxies, the temperature of this primordial radiation showed strange, localized ripples. These were not the gentle, predictable fluctuations expected from a smooth, expanding universe. They were sharp statistical anomalies, unexpected hot and cold spots that our best models of cosmic inflation could not explain. To a cosmologist, these patterns are like finding a sudden, unexplained gust of wind in a room sealed for billions of years. The only logical source for such disturbances is an unseen energy source or a hidden form of matter interacting with this ancient light. The debate this sparked was fierce, challenging one of cosmology's core principles, the assumption that on the largest scales, the universe is homogeneous. How could the universe be truly smooth if its oldest light tells a story of hidden structures warping the void? This clue, written in the faint whisper of creation's first heat, forces a profound realization. The shadows we called empty are not inert. They are subtly but unmistakably imprinted with the signature of something we have yet to see. While the cosmic microwave background revealed a hidden texture, a second clue arrived by watching light bend in the dark. Astronomers tracking the brilliant, distant beacons known as quasars noticed something deeply strange. The light from these objects was being subtly warped and distorted as it journeyed across billions of light years to reach our telescopes. This phenomenon, called gravitational lensing, is like seeing a distant street lamp shimmer through the heat rising from a desert road. It happens when the fabric of spacetime itself is bent by mass. The profound mystery, however, was the location of this distortion. The quasar's light was not being bent by a visible galaxy or cluster. It was warping as it traversed the immense, supposedly empty cosmic voids. This weak lensing effect, meticulously measured by projects like the Dark Energy Survey, acts as a cosmic scale. It is weighing something invisible. The calculations are undeniable. They reveal vast amounts of unseen mass smoothly distributed throughout these voids, a shadowy substance that does not clump around galaxies but instead permeates the nothingness. One leading cosmologist described the finding as a direct challenge to our textbooks, stating, "Our models of mass distribution are fundamentally incomplete if the voids are this heavy." This clue forces a difficult question. What form does this mass take? It could be an incredibly diffuse sea of dark matter, a component of the mysterious substance that refuses to gather where we expected it. Or perhaps it is a population of ancient primordial black holes floating like invisible icebergs in a dark sea. Either possibility reshapes our understanding. The emptiness, it seems, is not empty at all. It is weighed down by a ghostly presence, a hidden architecture that guides light itself on its long journey through the dark. The silence of the void was broken by a cosmic scream. In 2007, astronomers sifting through old data stumbled upon a burst of radio waves so powerful it released more energy in a millisecond than our sun does in 80 years. This was the first detected fast radio burst, a split-second event that seemed to come from nowhere. Since then, hundreds more have been recorded, and a specific, baffling subset originates from the deepest, darkest intergalactic spaces, far from any visible galaxy. These are not just random blips, they are precise, energetic messengers traveling for billions of years across the cosmic voids we once thought were barren. The journey itself is a clue, as the radio waves are stretched and dispersed by the tenuous matter they pass through, allowing scientists to measure the hidden content of the void. Each burst that arrives from the great dark is like a probe sent back from an unexplored continent, reporting on the landscape it crossed. The source of this immense energy remains one of astronomy's greatest puzzles. Could they be the final, dying cries of collapsing magnetars, which are neutron stars with unimaginably powerful magnetic fields? Or perhaps they are produced by cosmic cataclysms we have not yet conceived, involving theoretical structures like cosmic strings, flaws in the very fabric of spacetime. This clue transforms our perception completely. The voids are not passive backdrops, they are active cosmic arenas, hosting some of the most violent and enigmatic events in the universe. What other titanic forces are at play in the shadows, announcing their presence only in fleeting, brilliant shouts? For all the matter we know should exist, half of it is simply gone. This is the missing Baryon problem, a cosmic accounting error that has haunted astronomers for decades. Baryons are the particles that make up everything we can see, from stars and planets to our own bodies. When we tally up all the ordinary matter that should have been created in the Big Bang, our observations of galaxies and clusters come up short by nearly 50%. It is as if half the building blocks of the visible universe have vanished without a trace. The most compelling solution to this mystery lies hidden in the very voids we once dismissed. Theorists propose that the missing matter could be spread out in a vast, diffuse web of superheated gas, a structure they call the warm-hot intergalactic medium, or WIM. Imagine a cosmic fog, so thin that a single cube of it the size of Earth would contain less gas than the air in a child's balloon. This is not a cloud you could see or fly through. It is a ghostly filament of matter, ionized and shimmering with immense heat. Proving its existence required looking with the right eyes, and that meant turning our most powerful X-ray telescopes toward the deepest, darkest voids. Instruments like the Chandra X-ray Observatory have now detected the faint, telltale glow of this incredibly sparse gas. The signal is incredibly weak, a whisper of X-rays against a noisy background, but it is there. These observations suggest that the whim, woven through the cosmic voids, could account for all the missing ordinary matter in the universe. This single clue completely reframes the purpose of these vast empty spaces. They are not barren wastelands, but the universe's hidden reservoirs, holding in a near-invisible form the very stuff that builds galaxies and worlds. The darkness between the stars is not empty at all. It is a cosmic treasury, safeguarding the fundamental ingredients of reality itself. Deep within the cosmic voids, where our telescopes expected to find nothing but a perfect vacuum, they instead found lonely clouds of hydrogen. These are not the bright, star-forming gas clouds we see within galaxies. They are isolated, primordial ghosts, drifting in the immense darkness with no stars to illuminate them. Their discovery came through a very specific kind of observation, the search for the faint radio signal emitted by neutral hydrogen atoms. This signal, known as the 21-centimeter line, acts like a cosmic tag, allowing astronomers to pinpoint the location of cold gas even in the blackest emptiness. Massive surveys like Alfalfa, which methodically scanned the sky for this specific whisper, began to map these solitary clouds. They found them floating freely, vast reservoirs of the universe's most basic building block, completely detached from any galactic structure. This presents a direct challenge to our understanding of how galaxies grow. The prevailing model suggests that galaxies are not isolated islands, but are constantly fed by streams of fresh gas, a process called gas accretion, flowing in along the cosmic web. But these clouds are not flowing anywhere. They are simply adrift like unclaimed building supplies scattered across a vacant lot. How did they get there, and why have they not collapsed to form stars? Their very existence suggests that the process of gas accumulation is far more chaotic and less efficient than we thought. Some of these hydrogen ghosts could be the shredded remains of ancient, failed galaxies, torn apart by gravitational forces eons ago. Others might be pristine pockets of gas that have simply never felt the trigger to collapse. They are silent testimonies to a history of cosmic evolution that left countless possibilities unfinished. What other relics of forgotten processes are hiding in the dark, waiting for us to learn how to see them? Galaxies on the edge of the void are fleeing from something we cannot see. We have long understood that the universe is expanding, with most galaxies moving away from us in a smooth, predictable flow governed by Hubble's law. Their redshift, the stretching of their light toward the red end of the spectrum, is a cosmic speedometer reading, but for galaxies skirting the boundaries of immense voids, that reading makes no sense. Their redshifts are anomalous, telling a story of motion that defies the simple expansion of space. These galaxies are not just riding the cosmic tide, they are sprinting with a peculiar velocity of their own. This movement is a direct tracer of gravity, a cosmic tug of war playing out in the darkness. The only force that can impart such a peculiar velocity is a significant gravitational pull, and the direction of their motion points a collective finger back toward the heart of the void they are supposedly escaping. It is as if every ship at the edge of a calm sea is suddenly leaning away, pulled by an unseen current flowing from the depths. This implies that the void itself is not a region of nothingness, but contains a large-scale distribution of mass whose gravitational influence is actively shepherding these galaxies. Our current maps of mass, based on visible structures, completely fail to account for this motion. The invisible hand guiding these galaxies could be a vast, diffuse halo of dark matter, a gravitational skeleton within the void that our telescopes have missed. Or it might be evidence of something even more exotic, a modification to the laws of gravity itself on the largest scales. Either way, the frantic flight of these edge-dwellers reveals a profound truth. The greatest gravitational influences are not always where the light is brightest. They can emanate from the silent, dark heart of nothing, pulling the strings of the cosmic dance from the shadows. These isolated dwarf galaxies are cosmic relics frozen in time. The hierarchical model of galaxy formation told a simple story, that large galaxies like our Milky Way grew over billions of years by consuming smaller ones, a process of cosmic cannibalism. In this model, the vast void should be the ultimate galactic deserts, regions where gravity never got a foothold and structure failed to form. Yet, when we finally looked deep into these voids, we found them teeming with faint, irregular galaxies. They are not the grand spirals we are familiar with, but small, misshapen, and pristine collections of stars and gas. Their existence is a direct paradox, a clue that the voids are not the sterile wastelands we presumed. These galaxies are the underdogs of the cosmos, and their survival tells a new story. They possess uniquely primitive qualities, like very low metallicity. In astronomy, metallicity does not just refer to metals, but to any element heavier than hydrogen or helium. These elements are forged in the hearts of stars and scattered by supernova explosions. A low metallicity means a galaxy is made of mostly pure, unprocessed material, a sign that it has experienced very few generations of stars. These void dwarfs are like isolated tribes that have never encountered the Industrial Revolution, living in a state that reflects the early, simpler universe. They are also incredibly gas-rich, brimming with the raw hydrogen fuel for star formation, yet they form new stars at an achingly slow pace. It is as if they have all the ingredients for a fire but lack the spark to make it roar. This slow, quiet evolution challenges the idea that galaxies need to be in the busy, violent environments of clusters to evolve. Here, in the profound quiet of the void, galaxies can exist in a state of suspended animation, largely untouched by the gravitational turmoil and galactic collisions that shape their cousins in denser regions. Their mere presence forces a profound question. How did these fragile structures survive the pull of larger galaxies? Why did they not get consumed or ripped apart? Their continued existence suggests that the voids are not just empty space but protective bubbles, shielding these ancient, slow-living galaxies from the aggressive evolution happening elsewhere. They are living fossils, and by studying them, we are not just looking at failed galaxies. We are looking back at a quieter, more isolated path that cosmic evolution can take. Here we find the universe's greatest missed connection. For decades, we assumed that dark matter and visible matter were inextricably linked, that every vast, invisible halo of dark matter would, at its center, host a shining galaxy. This was the foundation of our cosmic model, but the voids have delivered a clue that shatters this partnership. Advanced computer simulations of cosmic structure, which model how dark matter should clump under gravity, predict a startling abundance of pure dark matter halos. These are concentrated islands of the invisible substance that, for reasons unknown, never managed to attract or retain the ordinary gas needed to spark a single star. They are gravitational ghosts, massive structures with no light to call their own. We cannot see them directly, but their presence is felt. The subtle, persistent, weak gravitational lensing we observe across vast, dark patches of sky requires more mass than any visible structure or diffuse gas can provide. Furthermore, the specific patterns of ripples in the cosmic microwave background, align perfectly with models that include a large population of these dark halos scattered throughout the voids. Their gravitational influence is subtly imprinted on that ancient light. What does this mean for the relationship between dark and ordinary matter? It suggests a profound divorce. The presence of dark matter does not automatically guarantee the birth of a galaxy. Some essential trigger was missing in these voids, perhaps a critical density of gas or a specific gravitational nudge that never occurred. These dark halos are the universe's unfinished projects, skeletons of galaxies that never were. They reveal a hidden architecture of pure gravity, a shadow framework that exists completely independently from the luminous universe we see. This forces a humbling question: how many of these invisible islands are out there? Could our own Milky Way, with all its billions of stars, be orbiting one of these massive, completely dark halos, a silent partner in our cosmic dance that we have never even noticed? The universe also fires its most energetic bullets directly from the void. These are ultra-high energy cosmic rays, subatomic particles accelerated to a fraction of the speed of light, each carrying the punch of a professionally thrown baseball. For years, their origins were a total mystery, their paths scrambled by magnetic fields as they crossed the cosmos. But massive observatories like the Pierre Auger Observatory, with its thousands of square kilometers of detectors, have begun to map their arrival directions with enough precision to reveal a subtle pattern. The distribution is not perfectly random. It shows slight but significant anisotropies, meaning these particles are not arriving evenly from all directions. The most baffling part is that some of these preferred directions align not with brilliant quasars or active galaxies, but with the locations of some of the largest, darkest cosmic voids. This correlation is a profound puzzle. How could a region we thought was a near-perfect vacuum be the source of the most energetic particles in existence? Tracing a cosmic ray back to its source is like trying to find the origin of a single bullet fired in a hurricane. The path is bent and twisted beyond recognition. Yet the statistical evidence points insistently toward the emptiness. This forces two radical possibilities. First, the voids themselves could be cosmic accelerators. Perhaps immense, undiscovered magnetic fields that span millions of light-years are woven through the void, capable of whipping particles up to these unbelievable energies. Or second, the voids are not empty at all, but contain a hidden population of unknown sources. These could be exotic objects like decaying super-heavy dark matter, or engines of a type we have not yet conceived, operating in perfect darkness. This clue transforms our view once more. The voids are not passive. They are either actively manufacturing the universe's most extreme particles, or they are dense with invisible power plants, their presence betrayed only by the subatomic shrapnel they fire across the cosmos. A subtle cosmic chill confirms the void is not what it seems. As the ancient light of the cosmic microwave background travels for billions of years to reach us, it passes through every structure in its path, including the vast, expanding cosmic voids. When a photon enters one of these voids, it must climb out of a gravitational well. In a universe dominated by matter, the well would deepen as the photon struggles upward, stealing its energy and making it appear cooler. But we are not seeing that. Instead, measurements show these photons are arriving slightly warmer, as if they gained a tiny bit of energy on their journey. This is the integrated Sachs-Wolf effect, a direct imprint of the universe's changing gravitational landscape. The only way a photon can gain energy climbing out of a well is if the well itself is becoming shallower as the photon travels. The void is actively being stretched and flattened by an unseen force. This is a stunning, real-time signature of dark energy at work. The correlation between the positions of the largest voids and these specific temperature shifts in the background radiation is statistically undeniable, a signal that has been confirmed by cross-referencing galaxy surveys with microwave maps. This clue transforms the cosmic microwave background from a static baby picture of the universe into a dynamic movie of its ongoing evolution. We are watching the fabric of the cosmos being actively reshaped, with the voids as the primary actors. The silent, empty spaces are not just there, they are expanding faster than everything else, their growth driven by the mysterious repulsive force we call dark energy. What does it mean that the greatest evidence for the universe's ultimate fate is written not in the galaxies, but in the relentless stretching of the nothingness between them? Even the cold darkness of the void holds a faint residual warmth. Space telescopes like Spitzer and WISE, designed to see the universe in infrared light, have mapped the deepest cosmic voids and found something they were never supposed to see: a persistent, diffuse glow. This is not the concentrated light of stars or galaxies, but a soft, omnipresent whisper of infrared radiation that seems to emanate from the emptiness itself. It is a background hum, a collective signature of countless unseen processes playing out over volumes of space so vast they defy comprehension. This glow is unresolved, meaning our most powerful instruments cannot pinpoint it to any single source. It is simply there, a faint warmth permeating the cosmic shadows. So what could possibly be producing this energy in a place we thought was barren? One compelling idea points to cosmic dust. When galaxies interact or collide, they can be stripped of their gas and dust, scattering these fine particles across millions of light years. This dust, drifting freely in the void, absorbs ambient starlight from the distant universe and re-radiates it as this faint infrared glow. It is the ghostly afterimage of ancient galactic disasters. Another, more exotic possibility involves the very fabric of reality. Certain theoretical particles, candidates for dark matter, are predicted to slowly decay over billions of years. The energy released from the decay of just a few particles across a cubic light year would be negligible. But when you multiply that by the incomprehensible volume of a cosmic void, the collective emission could manifest as this pervasive infrared background. It would be the slow, quiet death of the universe's hidden mass, making its presence known only as a subtle warmth. Or perhaps we are seeing the integrated light from the very first stars. These population 3 stars, hypothesized to be monstrously large and brilliant, would have lit up the early universe and then died long ago. Their combined ultraviolet light, stretched by the expansion of the universe over billions of years into the infrared, could now be reaching us as this diffuse background from the voids, a final, redshifted echo of the cosmos's first dawn. Each explanation carries a profound implication. The void is either a cosmic graveyard, filled with the dust of shattered galaxies, a slow-burning reactor fueled by decaying dark matter, or a museum displaying the faded light of the first stars. This unresolved glow is not a minor anomaly. It is the collective whisper of the void's hidden history, a story of loss, decay, and creation written in a language of heat we are only just learning to read. The faint warmth of the void is not its only hidden property. Woven through this apparent emptiness are the faintest threads of magnetism, a cosmic fabric stretching between the galaxies. These are not the powerful fields we find around stars or galaxies, but incredibly weak and diffuse magnetic fields that permeate the deepest voids. We cannot see them directly, but their presence is betrayed by the behavior of other cosmic travelers. When ultra-high energy cosmic rays journey across billions of light years, their paths are not perfectly straight lines. They are bent and twisted by these invisible magnetic threads, creating a subtle scattering pattern that reveals the field's existence. Similarly, the polarization of radio waves from distant quasars is rotated as it passes through the void, a phenomenon known as Faraday rotation, which acts as a direct probe of the magnetic environment it crossed. These fields are unimaginably weak, millions of times fainter than a common refrigerator magnet, yet they are coherent over scales so vast they defy human comprehension. How did such immense magnetic structures form? Their origins are a deep puzzle. One theory suggests they were born in the universe's first moments, seeded by the violent processes of cosmic inflation, and then stretched to cosmic proportions as space itself expanded. Another idea points to galactic winds, the immense outflows from supernova and active galaxies, which could have blown magnetic fields like cosmic breath into the voids, seeding them with these faint lines of force. A third possibility is that they were generated by processes in the early, hot plasma of the universe before the first stars ever ignited. Regardless of their source, their existence is revolutionary. These magnetic fields are a cosmic connective tissue, a subtle force that links one galaxy to another across the gulf of nothingness. They suggest that the voids are not just passive expanses, but are dynamically structured, threaded with invisible lines of influence that may have guided the formation of the cosmic web itself. What other invisible forces are at work in the dark, silently shaping the universe from behind the scenes? Light itself becomes a probe in the cosmic darkness, revealing anomalies we cannot explain. When the most powerful explosions in the universe, gamma-ray bursts, send their light screaming across billions of light-years, we expect it to be gradually dimmed. This fading should happen as the high-energy gamma rays collide with the fog of starlight that fills the cosmos, the extragalactic background light, losing energy in the process. But telescopes like the Fermi Large Area Telescope have observed something deeply strange. When these gamma rays travel through the largest cosmic voids, they arrive brighter and more intact than any standard model predicts. The universe, in these specific corridors of emptiness, is far more transparent than it has any right to be. It is as if a searchlight beam, expected to be swallowed by a thick fog, instead passes through a perfectly clear tunnel. This is the void transparency test, and it is failing in a way that points to revolutionary physics. One extraordinary explanation involves hypothetical particles called action-like particles. These are lightweight, ghostly particles predicted by some theories beyond the standard model. The gamma rays, in the presence of the weak magnetic fields we know thread the voids, could be momentarily transforming into these action-like particles. In this form, they would travel completely unimpeded through the background light, as ghosts walking through walls, before transforming back into detectable gamma rays near the end of their journey. This oscillation would create the illusion of a more transparent universe. Another possibility is that our entire understanding of the extragalactic background light, the cosmic fog itself, is fundamentally wrong, and its density in the voids is far lower than we have calculated. Either scenario is profound. We are either seeing the first direct evidence for a new fundamental particle, a component of the dark sector, or we have grossly misjudged the true distribution of starlight across cosmic history. This clue, written in the unimpeded journey of the universe's most energetic light, tells us that the voids are not just empty space, but laboratories for physics we have not yet discovered. What other fundamental laws are being rewritten in the quiet darkness between the stars? Our cosmic maps are in motion, and they are moving in ways that should be impossible. Across billions of light-years, entire superclusters of galaxies are drifting like leaves on a river caught in a current we cannot see. This is not the smooth, predictable expansion of the universe, but a vast, coherent drift known as a bulk flow. Astronomers measure these motions by calculating the peculiar velocities of thousands of galaxy clusters. comparing their observed movement against what is expected from the expansion of space alone. The results are startling. These immense rivers of galaxies are not flowing randomly. They show a distinct preference, often moving collectively toward or away from the largest cosmic voids. This is like watching every ship in an ocean suddenly lean in the same direction, pulled by a tide emanating from the deepest, emptiest part of the sea. According to our standard model of cosmology, lambda CDM, such enormous, coordinated motions should not exist on these scales. The gravitational pull from the visible matter in the voids is far too weak to account for this drift, and the influence of dark energy should be creating a more uniform, outward expansion. The presence of these bulk flows creates a direct tension with our understanding of how dark matter and dark energy sculpt the cosmos. It suggests that the mass we have mapped, both seen and unseen, is not enough to generate this motion. There must be an additional gravitational source, a pull from something immense that lies beyond our current field of view. This points to influences from beyond the observable horizon, from cosmic structures so vast and distant that their light has not yet had time to reach us. Their gravitational shadow, however, is already here, tugging at the fabric of our local universe and steering its largest components. The silent voids are not just features of the cosmos. They are the windows through which we feel the pull of the unseeable, the hidden geography of the universe that lies just over the edge of our vision. Floating in the ancient glow of the cosmic microwave background is a profound chill, a patch of sky so inexplicably cold it defies simple explanation. This is the cold spot, a vast and anomalous region in the universe's first light that is significantly cooler than its surroundings. For years, its existence was a major puzzle, a blemish on the otherwise smooth infant portrait of our cosmos. Then, astronomers mapping the large-scale structure of the universe found a clue in the darkness, a corresponding supervoid, an immense and largely empty region of space, sitting directly along our line of sight to this cosmic cold. The initial thought was that this solved the mystery, connecting two of our clues through the integrated Sachs-Wolf effect. As the CMB photons passed through this expanding supervoid, they would have to climb out of a gravitational well that was becoming shallower due to dark energy, losing extra energy and thus appearing colder. It was a perfect, elegant link between the universe's oldest light and its modern emptiness, but the math did not add up. The observed supervoid, while enormous, is simply not vast or empty enough to account for the profound coldness of the spot. The calculated energy loss is too small, the observed temperature drop is too large. This discrepancy ignited a fierce debate that continues today. Is our understanding of the ISW effect flawed, or are we misjudging the true scale of the void? Perhaps the supervoid is just the visible tip of a much larger, even emptier structure that our galaxy surveys have not yet been sensitive enough to detect. The other, more exotic possibility is that the cold spot is not caused by a void at all, but by something far stranger, a relic from the universe's birth known as a cosmic texture. Theorists propose that as the infant cosmos cooled and underwent phase transitions, flaws could have formed in the fabric of spacetime itself, like cracks forming in ice. A cosmic texture would be a specific type of topological defect, a knot in the fundamental fields of the universe. If such a knot existed and then unraveled, it would have released a tremendous burst of energy that would imprint itself on the cosmic microwave background as a permanent, circular cold spot. This clue forces us to confront two radically different universes. In one, the cold spot is a testament to the ultimate power of dark energy and the voids it dominates, a signature written in cold by the relentless stretching of nothing. In the other, it is a fossil, a scar from the violent processes that shaped reality in its first moments. Both possibilities are humbling. one suggests our maps of the cosmic web are still woefully incomplete, missing the true giants of emptiness. The other suggests we are seeing the ghost of a cosmic wound, a defect in spacetime that has been frozen in the sky for 13.8 billion years. Even the steady ticking of the universe's most reliable clocks is distorted by the void. Type 1, a supernova, are the gold standard of cosmic distance measurement, brilliant explosions of white dwarf stars that all reach the same peak brightness. Because we know their true luminosity, we can use them as standard candles to measure vast distances across the cosmos. Their light curves, the precise way they brighten and fade over weeks, are as predictable as a metronome. Yet, when astronomers observe these supernovae located far behind the largest cosmic voids, they sometimes detect a subtle but persistent anomaly. The light curve appears ever so slightly stretched, as if time itself is flowing at a different speed within that vast emptiness. This is a time dilation effect, a direct prediction of Einstein's theory of general relativity. According to relativity, time slows down in a stronger gravitational field and speeds up in a weaker one. A supernova's light, traveling for billions of years through a region of profound underdensity, is essentially climbing out of a shallow gravitational well for its entire journey. In this environment of incredibly weak gravity, time should run faster relative to the denser regions of the cosmic web. The light we receive from these distant explosions should therefore appear to evolve more quickly, not more slowly. The observed stretching is the opposite of what we'd expect from the void's gravity alone, creating a fascinating puzzle. The challenge in measuring this is immense, like trying to detect if a song played in an empty cathedral lasts a fraction of a second longer than the same song played in a crowded city. It requires comparing thousands of supernova light curves and meticulously accounting for every other possible factor. This anomaly forces a profound question. Is our understanding of general relativity, tested so perfectly within our solar system, beginning to fray at the edges when applied to the largest, emptiest scales of the cosmos? Could the gravitational potential of a void dominated by dark energy create a more complex distortion of spacetime than our equations predict? Or is this stretched light a hint of something else hidden within the void, an unseen mass or energy that warps time in a way we do not yet understand? This clue uses the universe's most trusted explosions to test its most fundamental laws, and in the quietest places, it hears a faint, discordant note. The universe's most elusive particles are now whispering secrets from the void. For decades, the Ice Cube Neutrino Observatory, a colossal detector buried deep in the Antarctic ice, has been patiently listening for these ghostly messengers. Neutrinos are near massless particles that barely interact with anything, allowing them to travel in perfectly straight lines for billions of years, completely unaffected by magnetic fields or interstellar gas. They are the ultimate cosmic couriers, carrying unaltered information from the most violent events in the universe. The immense challenge of neutrino astronomy lies in their ghostly nature, requiring instruments as vast as a cubic kilometer of ice just to catch a handful of these particles each year. But as the data accumulated, a subtle, tentative pattern began to emerge in the chaos. When researchers plotted the arrival directions of the highest energy astrophysical neutrinos, they noticed a faint but statistically intriguing correlation. A number of these particles seemed to originate not from brilliant galaxies or flashing quasars, but from the locations of some of the largest cosmic voids. This is a baffling connection, a whisper from the densest environments seemingly hidden within the emptiest places. What could possibly be creating these high-energy neutrinos in a near-perfect vacuum? Neutrinos are not produced by simple processes. They are born in the most extreme particle accelerators imaginable, typically in environments of incredible density and violence, like the cores of collapsing stars or the disks of supermassive black holes. Their detection from a void shatters that expectation. A confirmed correlation would force a radical rethinking of particle acceleration itself. It suggests that the voids contain hidden cosmic engines, perhaps immense magnetic reconnection events happening on scales of millions of light years, or a dense population of shrouded sources like blazars whose jets are pointed away from us, rendering them invisible in every other wavelength of light. The most profound possibility involves dark matter. If certain theoretical heavy dark matter particles were to accumulate and annihilate within the vast gravitational wells of pure dark matter halos in the voids, the resulting cascade of particles would produce a steady stream of high-energy neutrinos. In this scenario, the voids are not empty at all, but are dense with the invisible wreckage of dark matter, its presence betrayed only by the ghostly particles that escape its final destruction. These neutrinos are the perfect spies, reporting from the heart of the darkness without ever being seen. They tell us that the great voids are not just passive emptiness, but are active, energetic frontiers, hosting processes of creation and destruction that we are only beginning to fathom. These cosmic voids are not drifting passively, but actively carving their mark on the luminous universe. The true power of emptiness is revealed not at its center, but at its edges, where the sharp boundary between nothing and everything forms intricate structures known as void walls and filaments. These are the dense, bright membranes that contain the cosmic web, and their very shape tells a story dictated by the void within. Picture a balloon inflating inside a soft, wet clay. As the balloon expands, the clay is not just pushed aside, it is compressed, stretched, and molded into a specific shape around the growing emptiness. This is precisely what cosmic voids do to the matter surrounding them. The relentless expansion of a void, driven by its own underdensity and the push of dark energy, exerts a powerful influence on its borders. Galaxies caught in these walls are not randomly scattered. They are arranged into vast, flattened sheets and elongated threads, their patterns directly sculpted by the void's outward pressure. We can see the results in galaxy redshift surveys, which map the three-dimensional positions of millions of galaxies. The structures surrounding the largest voids consistently show this compressed, sheet-like morphology. The voids are not just empty spaces, they are cosmic sculptors, pressing the universe into a specific architecture. Computer simulations of cosmic evolution vividly demonstrate this process. When scientists run models that include the dynamic influence of dark energy-driven void expansion, the virtual universe that emerges perfectly mirrors the thin walls and delicate filaments we observe. In simulations that ignore this active sculpting, the cosmic web looks different, blobbier, and less defined. This tells us that the sharp, geometric beauty of the cosmic web is a direct product of the voids that define it. The walls are a record of the void's growth, a frozen moment of compression that reveals the history and strength of the emptiness they contain. The density of galaxies within these walls is another crucial clue. In a static universe, we might expect matter to simply pile up at the edges of a void. But observations show something more dynamic. The walls are often sharper and more defined than gravity alone would allow, as if the matter is being actively squeezed into a thinner layer. This suggests that the void is not merely a passive absence, but an active force, evacuating its interior and piling that material up at its edges in a specific, compressed configuration. So the next time you see a map of the cosmic web, do not just look at the bright knots of galaxy clusters. Look at the dark patches, See how every empty space is perfectly framed by brilliant, sharp-edged walls. This magnificent, luminous tapestry is not hanging in a void, it is being woven by one. The silent, expanding nothingness is the master architect, and the entire structure of the visible universe is its lasting impression. Even the vacuum of space itself may not be truly empty in the voids. Beyond the hidden matter and energy, we must confront the strange possibility that the nothingness has a fundamental structure. This brings us to the quantum realm, where the concept of a perfect vacuum dissolves. According to quantum field theory, what we call empty space is a seething, bubbling foam of virtual particles. These are pairs of particles and antiparticles that pop in and out of existence for impossibly brief moments, borrowing energy from the universe before annihilating each other and paying it back. This perpetual dance is not just a mathematical curiosity, it has real, measurable consequences. In our laboratories, we see this as the Casimir effect. When you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they are gently pushed together. Why? Because the narrow gap between the plates restricts the kinds of virtual particles that can appear there, while outside the plates, the full spectrum of fluctuations can occur. The greater pressure from outside forces the plates together. It is a tiny quantum force born from the energy of nothing. Now, expand this idea to a cosmic scale. A cosmic void is the most immense low-density environment we know. With so few atoms and so little radiation, the quantum vacuum there is far less disturbed than it is in the crowded space within a galaxy. This means the properties of the vacuum itself, its innate energy density, could be different. In the profound quiet of a void, the quantum fluctuations might be freer to express themselves on larger scales, or perhaps their average energy is subtly lower. This is a deeply theoretical clue, but its implications are staggering. If the vacuum energy varies between a dense galaxy cluster and an empty void, it would mean that the dark energy driving the universe's accelerated expansion is not a constant, as we currently assume. Instead, it would be a dynamic property of space that changes depending on its environment. The void would not just be expanding, it would be expanding at a rate dictated by its own unique quantum vacuum state. This idea connects the very largest structures in the cosmos, the billion light-year-wide voids, to the very smallest, the Planck-length frenzy of the quantum world. It suggests that the ultimate fate of the universe may be written not in the language of galaxies, but in the silent, shifting energy of the deepest nothing. Our final clue may be the master key that unlocks many of these cosmic secrets. It takes us back to the very first moments after the Big Bang, to a time of unimaginable density and turbulence. In that primordial chaos, theorists propose that pockets of matter could have collapsed directly into black holes. Unlike the stellar black holes we know, which form from dying stars, these primordial black holes would have been forged in the furnace of creation itself, and they could be of almost any size, from smaller than an atom to more massive than a star. Vast populations of these ancient objects, formed before the first stars ever ignited, could have been naturally flung into the expanding voids during the universe's infancy, becoming the hidden seeds of today's cosmic emptiness. This single, elegant hypothesis could explain a stunning number of the anomalies we have encountered. Those unexplained weak gravitational lensing effects, where light bends in the dark, could be the collective gravitational pull of countless primordial black holes drifting through the void. They would act as invisible lenses, warping space-time without emitting a single photon. The frantic motion of galaxies fleeing the edges of voids could be driven by the combined gravity of these hidden masses, a vast, diffuse swarm pulling on the cosmic structures around them. They could even account for a significant portion, or even all, of the dark matter that has eluded us for so long, solving one of cosmology's greatest puzzles with objects that have been hiding in plain sight, or rather, in the dark. Some models even suggest that the collisions and mergers of these primordial black holes could be the source of the gravitational waves we are now detecting, and perhaps even power the mysterious fast radio bursts that echo from the deep dark. This idea ties the universe's largest mysteries to its smallest possible origins. It paints a picture of the cosmic voids not as accidental emptiness, but as territories claimed and maintained by a hidden population of the universe's oldest and most enigmatic objects. The great darkness between the galaxies is not a void at all. It is an archive, a preserve, a kingdom of ghosts from the first second of time, whose silent gravity still writes the rules for the cosmos we see today. This emerging picture completely rewrites the cosmic story. The 20 clues left in the shadows force us to abandon the very idea of emptiness. We now see cosmic voids not as barren wastelands, but as dynamic ecosystems, each with its own hidden physics and a profound role in shaping the universe. They are the universe's reservoirs holding the warm, diffuse gas of the missing baryons. They are the domain of invisible architects, populated by pure dark matter halos and perhaps swarms of primordial black holes. They are active arenas hosting the violent birth of fast radio bursts and the acceleration of ultra-high energy particles. They are cosmic sculptors whose expansion presses the surrounding matter into the sharp walls and filaments of the cosmic web. And they are fundamental laboratories where the transparency to gamma rays hints at new particles, and the subtle warmth suggests a quantum vacuum unlike any other. This integrated view shatters old paradigms. Galaxy formation is no longer a process contained within clusters, but a drama influenced by the gravitational tides and gas flows from the surrounding voids. The peculiar velocities of galaxies on the edge are not anomalies, but expected responses to the void's hidden mass. Dark energy is no longer just a uniform force, but a dynamic agent whose effects are most vividly recorded in the relentless stretching of these nothingnesses, imprinted on the ancient cosmic microwave background. The shadows between the galaxies are now illuminated as active, essential participants. They are not the empty stage, but co-stars in the cosmic play, their hidden actions dictating the arrangement of the luminous universe and perhaps holding the key to its ultimate fate. The great darkness is alive. Our journey ends not with a final answer, but with a new way of seeing. We have traveled through 20 profound clues, each one a testament to the vibrant life hidden within the cosmic shadows. From the subtle bending of light in the dark to the discovery of the universe's missing building blocks, from the faint warmth of primordial dust to the violent birth of fast radio bursts, every piece of evidence forces us to erase the word empty from our cosmic vocabulary. The voids are not barren wastelands, they are active, dynamic ecosystems that shape the very architecture of the universe. They are reservoirs, arenas, sculptors, and fundamental laboratories all at once. The universe's greatest secrets have always been waiting not in the brilliant islands of light, but in the quiet, whispering darkness between them. If this exploration has reshaped your view of the cosmos, we would love to hear your thoughts in the comments below. Consider subscribing for more journeys into the unknown. The next time you gaze up at the night sky, remember this new truth: the voids are speaking, and we are only just beginning to learn how to listen.